Welcome to the latest in our series of community Zoom webinars, where we highlight recent events at the Green Bank Observatory and a specific piece of research. Jim Jackson, our director, is in a meeting right now and can't attend, so he's asked me to say a few words in his behalf. And actually, we have very little to say right now. The telescope proposal TAC has met, and so there will be a director's review, and then the results of that process will be sent out to everyone who proposed in probably about 10 days, I think. We're also preparing for the single dish workshop in conjunction with our Arecibo Observatory. This is for your information only. We're oversubscribed, but it will be taking place May 14th and 22 the 21st. If you're interested in this sort of thing where you pick up a lot of very useful skills about using single dishes for radio astronomy, we will have others in the coming years. Let me introduce our speaker today. Jeff Hazboun from the University of Washington will be talking about monitoring the solar wind with pulsar timing array observations. Let me remind everyone, if you have questions, please submit them through the Q&A button on the lower right of your screen, and we'll go through those at the end of the talk. And also, this talk is being recorded, so you'll be able to watch it again at your leisure, I think as soon as tonight. Okay, Jeff, take it away.
All right, thank you so much, Jay, for the invitation to talk and the introduction. Just give me a second here to start showing everything and then get this into play mode. So as Jay said, I'm at the University of Washington, and I work in the Nanograv collaboration, which hopefully many of you have heard about. Let's see if I can make this thing disappear. Just get this window out of here. Which hopefully many of you have heard about, which is a pulsar timing array collaboration that takes almost all of our observations now at Green Bank. And so I'm going to talk about monitoring the solar wind with our pulsar timing observations, but I am going to start just with a little bit of introduction about pulsar timing arrays, because that's sort of where I started in this business and why we have this enormous and beautiful data set to begin with. So we use pulsars as detectors to look for black holes. These are images that are courtesy of an article that we recently released through the International Pulsar Timing Array, which is sort of a consortia of all of the pulsar timing arrays in the world. Through the International Pulsar Timing Array, we released a new paper about our most recent findings for gravitational wave background, which is the sort of hum from all of the binary supermassive black holes in the universe. And that's what we look for with pulsar timing arrays. The idea is being that these ripples in space-time travel to us from cosmological distances, and within our own galaxy, we use pulsars that are sort of on this half of the galaxy to look for those gravitational waves. And the effect that we're searching for is basically a Doppler shift. As the gravitational waves pass between us and a pulsar, the pulses from the pulsar change frequency. And that's what we're looking for. And it just happens to be that using enough pulsars and enough lines of sight gives us the right sensitivity to see the gravitational waves from supermassive binary black holes that are sort of at the end, the centers of merged galaxies. Every galaxy out there has a big supermassive black holes at its center. At least most of them seem to. Over galactic time, the galaxies merge, then those black holes end up in the centers of the galaxies. So that's why we have this data set. That's why we have an enormous amount of observing time at Green Bank. We used to have a good chunk at Arecibo as well, and some at the VLA. And we also are using now a lot of CHIME data as well. So this is just that result, just as a quick advertisement for that. So this is from the International Pulsar Timing Array again, which is the last reference on the bottom here. But the three oldest pulsar timing arrays, which is the Nanograv, the Parkes Pulsar Timing Array in Australia, the Parkes Observatory, and the European Pulsar Timing Array, which uses a number of observatories in Europe, all have seen what we call a common red process. And what we mean there is that we're starting to see power in the lowest frequencies of the signal that we're looking for. This plot on the left is basically a Bayesian spectrograph. These plots, you can see the furthest left blue plot is a pretty significant detection of some power at some amplitude. So at some frequency there, which is, let's see, that is probably like 1/20 years, 1/25 years. There's some amplitude. I've written it, its power. We calculate the power, but I've converted it into amplitude in terms of the residuals of our data. The main point here is on the right is this cartoon picture. We have some white noise floor, and what we expect to see is this red noise. By red noise, we mean something that has power at lower frequencies. And you can, if you compare the right cartoon, where that red signal is what we're looking for, to the left real data analysis, then you can see there's this white noise floor at the high frequency end, and that there seems to be power emerging at the lowest frequencies. This is not enough to say we have a gravitational wave detection. We're just starting to see this power that seems to be the same. We're modeling it the same way in all the pulsars. We're not seeing the correlations we need to yet to claim that we see a gravitational wave background. Soon, though, we should have enough data to be able to say something like that. We expect to see this power before we see the correlations. So anyways, that's sort of a little advertisement for our recent PTA results. And again, this is sort of what we got, where we got started in all of this. I started by searching for gravitational waves. That's what my background is in. But I've become really interested in all of the stuff in between us and the pulsar, all of the noise sources, at least from the perspective of gravitational waves, all of the noise sources that we have to deal with. So when you're timing pulsars, you have to deal with fitting the full timing model. The biggest signal is the Romer delay from the Earth moving around the sun. So that's a big signal that we have to pull out. If the pulsar is in a binary, there's another Doppler shift that we have to pull out from that as well in the timing. If it's in a relativistic binary, we have to also correct for the fact that the orbit is changing due to emission of its own gravitational waves, which is a totally separate thing. And then there's all of the stuff in between, right? And so there's all of this interstellar medium, and it's the ionized interstellar medium, especially, that affects the radio signals that we're looking for. I'm sure that there are people in the audience who are much more expert at ISM studies than myself. I know a lot from the perspective of timing pulsars, and we're just working on lots of different ways to monitor this. And one of the ways we've done that is this model where we sort of bin observations. We try and take observations at both. We were taking them at L band and at 800 megahertz. And you take those two and you can fit for the dispersion you get from the interstellar medium. But sometimes those observations with the different receivers are not very close to each other. And so you can have little changes and you get errors in some of the measurements from the changes in the interstellar medium. Overall, the integrated column density of electrons from us to the pulsar, the DM that we measure is in parsecs per cubic centimeter. At the level of those units, it doesn't change, but at a level of about 10 to the minus 3, 10 to the minus 4, we do see changes, and those are important for our timing and to get that right. And we know there's this phenomenal paper, if you're interested in all of the signals that could get in the way of pulsar timing. Katerina Taburzi, along with a bunch of folks from the Parkes Pulsar Timing Array, wrote this paper in 2015, and it's a study of these noise processes. And these are just figures from her paper. And the idea here so let's start with the left, which is the power spectral density, are different various signals. And on the top, the dashed line is, the red dashed line is for gravitational waves. This is from her simulations. So again, you see that sort of white noise floor, then it increasing at the lowest frequencies. And on the bottom, and it's hard to see, is the light blue dot dash line is from the solar wind. There's a peak there at 1 over a year, and then you can see it's not as steep at the lowest frequencies, but there is power there. And this comes from mismodeling the solar wind. And then on the right are the spatial correlations, the gravitational wave background. There's a bunch of simulations on the left, and on the right is the average of all of those. And that curve is called the Hellings and Downs curve. That's the curve we expect to see, the correlations, the spatial correlations we expect to see in the pulsars from a gravitational wave background. The solar wind, if you put errors in and try and model what you get from that, again, on the left is a bunch of simulations, and on the right is sort of the average of all of those. You can see that there's some correlation. It doesn't look exactly like the Hellings and Downs, but it's not something we want to be in the way for when we're searching for those correlations. So it's really important to us to understand the solar wind and to try and mitigate any issues that we get from this, from the perspective of searching for gravitational waves. And of course, I became really interested in what pulsar timing arrays can do to actually monitor the changes in the solar wind. Now, monitoring the solar wind with radio sources is an old science in the sense of it's basically from the time that pulsars were first discovered. People have tried to use them. So this Councilman paper on the right, this is from an abstract of the Astronomical Society, but these very early observations were already trying to measure. There's down at the bottom here. You'll see it says 10 electrons per cubic centimeter as a first estimate of what pulsars can do. And on the left, this is this original paper by Hewish and Dennison, trying to use scintillation for quasars, distant quasars, to be able to measure what the electron density is. And that one's really interesting. Both of these were interesting, especially from the perspective that we could measure electron density outside of the ecliptic and look at higher latitude changes. And of course, scintillation measurements have gone on, not regularly since the 60s, but recently they've been pretty regular. There's especially some groups in Japan who do a lot of scintillation measurements. I should take a step back and say I am no expert in the solar wind. I am an expert in pulsar timing array data analysis. And so if I misspeak or say something a little bit off here, please correct me. I'd love to hear corrections and know of other work as we go. The paper that I'm going to talk about in a second has a lot of these references, but I've had a lot of help with people who are more expert at this. Okay, and of course, measuring electron density in situ has been done by a lot of space missions, and there's been some missions like Ulysses have looked at higher latitudes for the sun. Many ACE, for instance, sits in the ecliptic basically, so we can measure the electron density there. Those are in situ measurements. The Viking mission actually did this phenomenal, neat measurement where they used a radio signal at 2 different frequencies to try and look at the changes in the solar wind, to look at the changes in the electron density as well. So again, this is an old game using radio to understand this. And so the signal that we're looking for here at the top, is the change in time of our pulses. And then that is dependent on the frequency, the new 1 over nu squared. And so lower frequencies appear later than higher frequencies, and it's dependent on these constants of nature, which is that first fraction, and the dm. And this is the dispersion measure. The dispersion measure is the integrated column density of electrons along the line of sight to our pulsars. And so what we can do is take this, so that's the top right, the dm. This is the very first line there is actually completely generic. You change the limits of integration. The next line down on the right, this is the classic model for sort of free-flowing solar wind that dies as 1 over r squared as you go away from the sun. You can calculate what the dispersion measure is then dependent on the electron density and basically the angle between the sun and the pulsar on the sky from Earth, right? So that's this theta. And so this gives you this dependence, which has been in all of the pulsar timing codes for a long time, which is theta over r sine theta. And it gives you this cusp-like features. I'll show you an example in a second. You can generalize this, and people have generalized this in different ways. We wrote down a nice clean expression in the paper here for any 1 over r to the p fall off. So if I change this 2 to a p, you end up getting this more complicated expression down here, which of course simplifies to this for p equals 2. There's a hypergeometric function in there, but basically you can solve for this for any 1 over p, and it doesn't have to be an integer, it can be anything. And so this allowed us to fit for different terms. There's a lot of work. There's a couple of Yu et al. Papers from Parks that look at trying to model using scintillation data and trying to use various trackings of what's going on with the sun to try and predict what's happening. What we decided to do here was just take the power of our pulsar timing array software, which allows us to monitor all these pulsars at once, fit for all of these parameters, put these models into the stack that we have, this enterprise stack for looking for gravitational waves, turn the crank and see what we can get for the solar wind. I should say that the same data set that we worked on here, the Nanograv 11-year data set, was analyzed for various solar wind effects by Dusty Madison in a few years before us. There he was fitting for using our dispersion measure fit that we do in Nanograv, and using that as sort of his fiducial data. What we did is we went a step lower in the data chain and actually started with the times of arrival of our pulses and fit for all of the noise, the dispersion measure, and everything else all at the same time. So this is really one of the only results I'll show you from the paper. And I'm going to talk about a bunch of different effects here. So on the top, I know it's a fairly big, messy figure, but just to talk you through all of the things that are here. The green is binned data from the ACE the ACE observatory, that sits at the 1 point. So it's corrected for what the electron density would be if you use a 1/r² density to the Earth. And so it's binned by 3-month intervals. The green line shows you the median, and then the green shading shows you the error bars there. And then we've gone through and fit using the 11-year data set. The blue X's, the width again shows the 3 months, and the Y error bars show you the actual error in the measurement of the electron density. And the blue is just the fiducial 1/r² model. The orange shows a model where we use a second solar wind term that has a higher dependence. So it's actually 1/r to the 4.39, and this is motivated by various solar wind models, but it would be the next term. And we wanted to see what effect that would have. And you can see, in most cases, there aren't very many differences between the blue and the orange, at least not within the error bars. But there are 2 places where there are really small error bars. And I've lost my pointer here, but there are 2 columns of dots on the right. They're just to the right of the legend, one right before 2012 and one right after 2013. You can see that both the blue and the orange have really small error bars, but they're pretty far apart from each other. And this is interesting. We wanted to understand why this was the case. The orange sort of falls more in line with the ACE data, and the blue is reading much higher density. But when we take into account, this 1/r² that's a higher fall off, something that would be important when you're closer to the sun, you get the orange lines. Now, if you look at the plot below, these are 2 of the pulsars that we have that we measure that go closest to the sun, closest approach to the sun. And you can actually see, so this is just the geometric factor. If you look at the left here, this is just the geometric factor of how that geometric factor affects the column density that we're looking at. And you can see that in both cases, one of the pulsars has observations that are very close to the sun, actually within a few solar radii of the sun. And that's going on right here. And in fact, you can pull up coronagraph data for all of these. And in each of these, but all on the left-hand side, there's this white crosshatch, and the crosshairs, and that's where the pulsar was on that day. The first 2 are the orange pluses, and the one on the right is the blue cross. And you can see just day to day from the first and the second one, there are some decent changes in the streaming of what's happening at the sun. And you can imagine that those changes have an effect, but also we're very close to the sun. And we really know that the 1/r² model is not perfect. So we're seeing that this second term can help ameliorate some of those effects. Another interesting thing that we can see in this plot is that now these pretty much match within error bars, the blue and the orange, but they don't really match the ACE data. And remember that the ACE data is in the ecliptic, But the pulsar column density measurements that we're getting are in all different directions. Some of our pulsars are in the ecliptic, others are pretty far off of the ecliptic. So we're getting measurements at all different altitudes, basically, of the solar wind. And this is this really interesting paper. It came out actually only a couple days before I was going to post this on the archive. These folks, so Tokumaru is someone who has archived and taken a lot of the scintillation data that's used to measure the electron density. And these folks put together a 3D solar wind speed and density model based on the interplanetary scintillation. If you look at the dates where this circle or where this red ellipse is on the right, they match very well the sort of last big spike in solar wind density at higher latitudes in the plot on the left. And so I think that's really interesting that the ACE data is not matching the pulsar data. And I think that that's because we're starting to see that we're actually measuring things out of the ecliptic. So these are all just sort of early inklings of what we can be able to do with the pulsars and our data sets. So that's sort of a tour of to me, what was some of the most interesting results of the paper. One really interesting thing that we'll be able to do with this is that once we can pull out what's local from the solar wind by fitting that, because it is a deterministic signal in some sense correlated between the pulsars, then we can start to understand what's going on along the individual lines of sight to the pulsars and maybe start to be able to study the interstellar medium even better. There's lots of questions in the pulsar community about what the turbulence is. The turbulence Kolmogorov, which is sort of the sort of theoretical way that turbulence acts, or does it act in different ways than we might expect? This plot is for one of our best pulsars, at least it used to be one of our best pulsars. Now we're kind of angry with it because of these big dips that are pointed at here in blue. But there you can see the spikes from the solar wind, those are in orange. Then there's just this general chatter, that's from the interstellar medium changing over time. We're basically looking through some cloud and getting some scattering and changes in the dispersion measure. I should say on the y-axis here, this is the change in dispersion measure. The black here is the model we normally use in nanograv, where we have binned dates and try and put multiple receiver measurements within one bin. And the blue is the model that we can now use that includes the solar wind model that I've been discussing. So being able to pull all of these pieces apart allows us to kind of understand what's happening. These two big exponential dips that are being pointed out with blue, we wrote a paper about it thinking it was some sort of lensing event possibility. There's been another one that's been much bigger with a much larger profile change. And now we're worried that there's actually some intrinsic profile change to 1713, but it's really, we're having difficulty sort of pulling apart the signals. So again, being able to pull these pieces apart will help us help us to understand whether this is actually interstellar medium or something else intrinsic. Just a couple slides left here. One thing I wanted to say, there's been a lot of work with the LWA, and who can take they can take measurements at much lower radio frequencies of some of these pulsars. 0030, J0030 plus 0451 is one of our ecliptic pulsars. And I think the main thing to point out from this plot here is to say that all of the blue dots have error bars, but they're much smaller than the nanograv error bars just because you have these lower frequency measurements. Being able to put nanograv and LWA data together is just going to increase the lever arm. So being able to take L-band data at Green Bank or 800 megahertz and these really low frequencies with LWA that's pretty continual and maybe focused around some of the solar wind cusps like we see on the right side of the square inset will be really useful for us going forward. And I also just want to say that I think a lot of us are really excited about the wideband feed at Green Bay, because that's really gonna allow us to have a huge lever arm. We're never gonna have this issue again of having 800 megahertz data and L-band data that's not happening on the same day or within a couple hours of each other. They're gonna happen instantaneously all together, and that's gonna be really useful. Hopefully no one is treating the wideband feed as I just treated it, bouncing it onto this slide. So. Okay, so I just say thank you very much for all of your attention. I'm happy to have a discussion or take questions about any of this. This is the top picture here is a nanograv meeting that happened at Green Bank pre-COVID in the light, the golden history of our collaboration. And the bottom picture here is an IPTA meeting that happened in New Mexico. So, okay, thanks very much.
Thanks very much, Jeff, for an excellent presentation. Let me remind people you can submit questions through the Q&A box on the lower right. Just have a question about your paper is based, I guess, on the 11-year nanograv data.
That's right.
And what year are you up to?
We are processing the 15-year data set. We have there's a lot of working groups in nanograv, but the main pipeline, we have a bunch of pulsar timers, the actual radio astronomers who are experts at the pulsars, and then the folks who take that data and look for gravitational waves or other correlated signals. And that the 15-year data set has just passed from the timers to the folks who are doing the gravitational wave analysis. So we're getting really close to being able to look at that. We actually have, though, now that data set, it takes a couple years for us to process the data to refit all of the timing models and things like that. And so I think we have now almost 17 years of data.
Excellent, excellent. And just a question about the solar wind. The structures that you're seeing in the solar wind, kind of how big are they? What's the kind of time scale for their passage across a pulsar?
Yeah, so good question. And we're taking, you have to take into account how the line of sight is changing too. So, but in the paper, I was looking at resolutions. You can see both you can see much smaller timescale changes than what I was looking at. My motivation, again, what originally started at trying to mitigate some of the noise for gravitational waves, which are much lower frequency. So that big messy plot I was showing, those were 3-month bins. But there's these papers that use the scintillation work, and you can resolve down to a couple of hours if you're taking data at that cadence, if you have data for that kind of cadence.
And there's structure on those timescales.
There is, yeah.
Okay.
But you're taking a column density measurement, right? So you're really saying, well, there's some between us and the sun, and the sun going out the other side of the solar system, there's some change. And on that scale, on that size scale, there's always a little bit of a change.
Yeah. Are there any other questions? Here we come. Should NASA send a dedicated pulsar timing probe beyond the heliopause?
That's an amazing question. I think yes, absolutely. I mean, I think, how about a radio telescope on the other side of on the far side of the moon would be a good start. But I don't think that the interplanetary medium is our worst noise source. I think that it's much easier for us to predict that than it is to predict what's going in the interstellar medium, and especially if there are these funny lensing events happening. And unfortunately, once we get beyond the heliopause, we can't go in all the different directions. If we sent a radio telescope to every pulsar, that would be great.
Are there correlations from the 11-year solar cycle and the ISM electron density? I mean, are there correlations from the 11-year solar cycle in the ISM electron density?
Well, I don't know. So let's see. I can't imagine that the actual interstellar medium is correlated on what kind of scale that would be. But no, this is going to be, I do have here plotted the solar minimum from the 24 min and the 24 max, which roughly corresponds to, right in here, the minimum, what you see here, and the maximum, what you see here, which they definitely see in the scintillation modeling. And you could squint your eyes and maybe say that we're seeing some of that in this data. But I think we need to, the 11-year data set actually is only about a solar cycle long. So once we get more data, we might be able, if that's what the questioner is asking, we might be able to see some correlations between the solar cycles. But since we have, and in the paper, there's actually a figure where we fit 4 different sort of this is a binned model, but you can do the same sort of thing by fitting like using a Fourier basis. And you see that most of the power actually seems to be in something right around 1/11 years. But since the data set is that long, it's hard to say whether it's the data set, or once we have a longer data set, we can say more.
We have another question. How do these measurements compare to LIGO observations?
Great. So great question. So for, and I wish I had a sensitivity curve plot to show you, but LIGO is, if LIGO is the visible band, the gravitational waves they're seeing in the visible band, we're probably like in the microwaves somewhere, and for gravitational waves, and something that like BICEP 2 that's looking for primordial gravitational waves from inflation would be the radio. So we're just much lower frequencies, and we're looking for, our frequencies are nanohertz, hence the name nanograv. We're looking, so for 1/15 years, 1/30 years is where we see the biggest black holes, and that really is just that's how long they take to, well, it's actually 2 times their binary frequency, but that's the sort of scales that we look at. LIGO sees they see stellar mass black holes, so something between 10 to, they've seen up to 100 solar mass black holes, and they see neutron stars that are all coalescing. So they need to see something that's right about to coalesce as a binary, and that's when there's a lot of energy coming out of the system. For us, we're looking at these supermassive black holes, and they're very, very far from merger. So they're just sort of happily orbiting each other at that point.
Well, that's all the time we have today. I'd like to thank Jeff once again for his presentation and remind everyone that it will be available on our website shortly. I look forward to seeing you all here 2 weeks from now on May 11th, when we'll have a presentation by Dee Li of the National Astronomical Observatory of China, a unified description of fast radio burst polarization based on FAST and GBT joint observations. We look forward to seeing you then. Thanks and goodbye.
Thank you all.